what are these numbers? What can these numbers, what values can they take on? So let's say that x1 is equal to 50. So knowing that they sum to 100, then what values can x2 and x3 take on? Well, x2 can take on any value. It could be a positive value, it could be a negative value, it could be a decimal value, because we have 3 different components here, and so 2 of them are free to vary. But if we know then that the second number, x2, is equal to 40, then x3 cannot vary, cannot randomly vary. It has to be, in this case, 10, because they add up to 100. So that's the basic idea of what we mean by degrees of freedom. And so in inferential statistical analysis, what we're going to do is compare 2 or more statistics, or look at the relationship, the association or correlation of random variables. Or we're going to do a prediction kind of study where we have a prediction model where we want to predict some particular outcome given a set of predictor variables, or what we call covariates. And so basically the model here is that our dependent variable, or outcome variable, is a function of, or is modeled as a function of the independent variable or variables plus an error component. And so the dependent variable can be something like maybe blood pressure would be our dependent variable, and we want to look at what things might predict or be associated with blood pressure. Maybe our dependent variable is survival, death, or alive. And so we have a dichotomous variable there, and we want to look at a set of independent variables that might predict or might be associated with our dependent variable. When we decide which statistic to do, or what's the appropriate statistic, we also need to consider how our variables are measured, particularly our outcome variable or our dependent variable. And so the commonly or the common measurement scales that you see defined are, first of all, a continuous measurement where you have an infinite numerical scale and the distances between scale divisions are equal. So for example, if we look at height, or say, for example, we look at height in inches. So what we mean by scale equality here is that say the difference between 59 inches and 60 inches is the same as the difference between 71 and 72 inches. In other words, it's 1 inch. An ordinal scale is where we number our outcomes. They're numerical, they have a certain particular order, but the distances between them are not necessarily equal. And so some examples of ordinal numbers are like cancer stages or cancer grades, or maybe you have 4 cancer stages that are labeled 1, 2, 3, and 4, with 4 being the most severe or the worst. But the distance between the 4 different stages is not necessarily the same. And then we have just simple counts where we just count things, count occurrences. So an example here might be the number of infections in the ICU, or overall in the hospital, the number of infections. And that's usually associated with some time, like over a 3-month period or a 1-year period. Then we have nominal variables. where these are what we refer to as categorical. In other words, you might assign numerical values to them, but they don't have a numerical meaning. And so examples like this are gender or race, where our values are just labels. And then finally, we have what's called time to event data, where we actually have two different outcomes or two different variables. One, we have the time variable, which is continuous. And then we have the event, which is a dichotomous variable. The event either occurs or it doesn't occur. And so when we look at statistics that we're either estimating or whether we're doing inferential statistics, or we're looking at the relationships or associations, we need to consider what type of data that we have. Then also another aspect of consideration here is what is our research design? In other words, what is the question that we're asking? And how do we set up our research study to answer that question? And so the three primary categories here are retrospective studies, which are referred to as case control studies. In retrospective studies, you're taking a sample of, say, patients that have already been in the hospital and have been given some treatment, or they've looked at some particular outcome. Then the second one is a prospective or a cohort study that's where it's non-randomized. So this an example would be, say we're going to look at patients that say have a certain type of cancer. They're all at stage 1, and then we're going to follow them for a certain amount of time and look at the progression of cancer over time, and look at the variables that might be associated with progression. So that's what referred to as a prospective study, but in this case, we're not. They're not randomized to a, say, like a treatment or control. And then finally, and the strongest design as far as getting it, say, cause and effect, is the experimental design, where we actually randomize subjects or patients to, say, treatment groups. And so in our cancer study, maybe we have 2 different treatments, and we randomize patients to one treatment or the other. And so in this case, we would have a comparison of the 2 groups where we have randomized patients. And so in doing that, what we do when we randomize is that we essentially wash out any pre-existing differences that might have existed between the experimental groups. And so the experimental design, or oftentimes called a randomized clinical trial, is really the strongest one of getting at cause and effect or relationships. So when we design a study, what we are doing really is we want to answer our research question about a population of subjects or a population of patients. But of course, we don't have the resources to sample everybody in a population. Say, for example, our population might be all colon cancer patients. Well, there's no way that we're going to be able to sample everyone in the population. So what we're going to do is we're going to take a sample of that population, and sometimes, or a lot of times, if we have a randomized study, then the sample that we're going to take is going to be drawn at random. Now I put in more or less there because it's not truly random, because then if you're working with human subjects in medical research, for example, they have to consent to the study. And so it's possible that a person might not consent, so they're not in the study. So obviously they're not randomized to one treatment or another, for example. But generally, we can say that if we're doing a randomized clinical trial, then that we have set up our study so that we can come to a more certain conclusion than with the other types of research studies. But regardless of the type of study that we have, whether it's a randomized trial, a cohort study, or a case control study, the one thing that we can't really control is bias in estimation or the analysis from the sample. And we refer to this as random sampling variability, or more shortly, chance. So in other words, the patients that you select for your study, that you sample for your study from your population, there's always a possibility that random sampling variability is going to negate the results that we get. And so this is where statistics comes in, is basically quantifying the random sampling variability. And so it gives us an index of whether we could say that, well, the chance that random sampling variability has affected our results is very small, or maybe we can't make that statement. And so then we get into the concepts of statistically significant or statistically not significant. So let me give kind of a picture here of what we're doing. So we have our population here over on the left, and we assume that this population has some mean. We'll refer to it as mu. And so when we do our research, we say randomly sample, or maybe we don't randomly select, but we select a certain cohort from this population, and this is our research sample. And so this is the research sample is what we're going to base our conclusions about our study. If we have, say, 2 cancer treatments, which one worked better, or neither one of them worked, or they worked about the same. So the concept here of statistics that we're talking about is the idea that if you were to be able to draw an infinite number of random samples from the population, that the mean of all these samples would approach the population mean. Okay. And so what we're hoping is that the one research sample that we get in our study is representative of the population. In other words, the mean of our research sample is a good estimate of the population mean. And because, again, we don't have the resources to do this sort of thing here, where we draw an infinite number of random samples and then compute the population mean that way. We basically get one chance at it. So I have an example here from my diastolic blood pressure that we looked at several slides ago. And so what I've done is I've randomly sampled from the 144, and each time I've drawn a sample of size 5. In other words, 5 different blood pressures from that population of 144. And so what I've done for each random sample that I've drawn here, I've computed the mean of these 5 values that I got in my sample. And then I've ordered them from smallest to largest. And you can see that some of these samples are pretty close to the population mean, which you remember, or if you remember, was about 76. So we have several samples here where the sample mean is really pretty close to the true population mean. But there are some samples that are not. In other words, their mean is really different. It's much smaller or maybe much larger than the population mean. And so this shows us what can happen when we draw a sample, whether it's random or not, from a population, that the mean that we get hopefully is representative of the population, but it might not be. And so it's what we want to determine is how good of an estimate our sample is of the population. And so as you can probably imagine, the larger the sample, the more accurate the estimation of the population parameter. So in talking about variability, we've talked about the standard deviation. And so the standard deviation, as we've seen, is variability of data about its mean. When we talk about a sampling distribution, though, our standard deviation is termed standard error. And when you hear the term standard error, what we're talking about is variability of a statistic. So for example, the standard error of a mean is its standard deviation divided by the square root of its sample size. And so in our inferential statistics that we're going to look at, we're going to focus on the standard error because we're looking at sampling variability, which is dependent on the sample size. And so you can see here that for a mean, the standard error of the mean, as the sample size gets larger, the standard error becomes smaller. And so, as I said, the larger the sample size, the better your estimate. And that's quantified in terms of the larger the sample size, the less variability of the statistic that you get of the standard error. So I have a fairly busy slide here to sort of illustrate this, where I have samples of size 5 from my population of blood pressures. I've calculated the mean, and I've calculated the standard error of the mean. And then from this, I can get what's called a confidence interval. And so I've illustrated this both with the lower bound and the upper bound of my confidence interval. And then I've graphed this over here on the right. So I have values from 59 out to 95 here. And so what this represents for each particular sample is what's called the 95% confidence interval. And what this means is that over repeated sampling, 95% of the time, the confidence interval will include the true population mean. And so I've indicated that here by the X's, which is our population mean is 76. And so you can see that most of the confidence intervals that we have include the population mean, but there's a couple here that don't. And so the idea here is that our confidence interval is going to be, as I mentioned, dependent on the sample size. And so if we increased our sample size to, say, 10, then we'll divide our standard deviation by the square root of 10. So we'll get a smaller standard error than we do here. And so the confidence interval is going to be smaller. But the basic idea here is that the means of samples, if we were able to sample repeatedly, constitute a sampling distribution. And then the standard error of the mean, in this case, quantifies the variability of the sampling distribution. And we get a 95% confidence interval based on the normal distribution. And I'll have a picture of that in a minute. But basically, it turns out that 95% of the area under a normal distribution lies between -2 and +2 standard deviations. So if we take 2 times our standard error that we've calculated, then we get the upper and lower bounds of our 95% confidence interval. And so as I mentioned before, the mean of the sampling distribution, in other words, the mean of all these means over an infinite number, will approximate the true population mean. And the larger the sample size, the smaller the standard error. And so this is just in words here what I have in the illustration in the previous slide, that the idea is that over repeated sampling or over an infinite number of samples, a 95% confidence interval includes the true population mean 95 times out of every 100 random samples. So that was the, in calculating a standard error of the mean, I was using the normal distribution there, but there are other theoretical sampling distributions that are used in statistical analysis. And by these theoretical distributions, we mean that they are, that they have a mathematical formula. So because of that, then we can easily calculate areas under the curve and come up with probabilities of random variables for any given distribution. And so I'll just spend a little time here on the normal distribution, since that's probably more familiar with to everyone. So in a normal distribution, it's defined by 2 parameters, its mean and its standard deviation. And it's a symmetrical distribution, which the measures of central tendency, the mean, the median, and the mode are all equal. And so in this picture of a normal distribution, we can see this. So in this particular normal distribution here, I have a mean of 85 and a standard deviation of 5. And in a normal distribution, one standard deviation occurs at where the curve becomes or changes from convex to concave, or concave to convex, whichever way you're going here. So that's the definition of a normal distribution is really nice, has really nice properties. And it turns out that about 68% of the area under the normal distribution is contained in -1 to +1 standard deviations about the mean. And so when we then look at, as we did before, calculating 95% confidence intervals, it turns out that between -2 and approximately -2 and +2 standard deviations, we have 95% of the area under the normal curve. So that means that if that's the case, then we have 2.5% in each tail of the distribution here, each side of the distribution, 2.5% at -2 or less, and 2.5% at +2 or greater. And so that's where we are coming up with our 95% confidence interval, that we're saying that 95 times, or how we're calculating our confidence interval, the upper and lower bounds, is that we're taking the lower and the upper 2.5%. Okay, so then other theoretical distributions that we have that you may or may not have heard of, like a chi-square. Most everyone has probably heard of a chi-square distribution. We use that when we look at contingency tables or look at goodness of fit. Then a t distribution, which is symmetrical like a normal distribution. It just has thicker tails because it's dependent on sample size. But we use a t distribution to compare means and correlations. And then the F distribution that we use in looking at analysis of variance. And these distributions, there are other distributions, but these are the most common ones you'll see in statistics. They're sample size dependent, but for each one, as sample size tends towards infinity, the distributions become or tend to become normally distributed. So that then leads us to talking about statistical significance and p-values. And we're going to look at areas under the curve, these sampling distribution curves to come up with what we term statistical significance. And so in a very general, at a very broad level here, all statistical analyses involve two sources of variance of the outcome variable in the data. And so we have known variance, that's variance between, say, treatment groups or differences in ages, difference in race, or other variables that we may have in our analysis. And then there's unknown variance, which we refer to as error variance. And there's always error variance in any statistical test or any statistical model that we come up with. And basically a statistical test then, whether we are going to test whether something is significant or not significant, is basically our known variance divided by our unknown variance. And then the value that we get, the p-value that we get from this statistics of known variance over unknown variance, which will be one of the distributions, a normal distribution or t distribution or chi-square distribution. The p-value associated with that t statistics means the probability of obtaining a value of t or larger just by random sampling variability. So as probably most everyone is familiar with, the most common p-value that is used to define statistical significance in most areas of the literature of research studies is 0.05. And so what that means is that if you get a p-value of 0.05, that means that the probability of getting a t statistic or a larger one just by random sampling variability is only 5 out of 100 chances. Okay. If the p-value turns out to be, say, for example, 0.01, then that means that there's a chance that our test statistic occurred by random sampling variability just 1 out of 100 times. So we'll kind of get into some examples of this, but I wanted just to really emphasize this of what we're doing when we do statistical tests, or you see p-values associated with statistical tests. So let me give an example here of testing a hypothesis. And so let's say that I have two groups here of blood pressure values for my population. And I have a treatment group and a control group. And my sample of 5 patients in each. And so the mean of the treatment group is 81 and the mean of the control group is 86. And so what I'm interested in here is being able to say, well, did the treatment lower blood pressure? And so if I just look at the numbers as they are, I'd say, well, sure, it did. It's 5 points lower in the treatment group. But the problem is because these are samples, then there's variability associated with these means. And so the question I'm asking is the difference between 86 and 81 just random sampling variability, or can we consider it a real difference? And so in statistics, we have what's called the null hypothesis and the alternative hypothesis. And the null hypothesis is that there's no difference between them, these means. In other words, the 5-point difference here just occurred because of random sampling variability. Whereas my alternative hypothesis is which I hope to be able to show or to prove in a sense, that there is a difference between the means of the treatment and control groups, and that this difference is unlikely to have occurred just by chance. So in making our decision, our statistical decision here, we're going to start out by assuming that the null hypothesis is true. And so our statistical tests are going to give us the probability of attaining the value of the test statistic, or whichever that comes from, a t distribution or a normal distribution, by chance, and then by inference whether differences are what we call, or what is called statistically significant. And so when we do hypothesis testing, we can illustrate the decisions that we make in this little table here, where the rows represent the decisions that we make based on our statistical test from our samples, and the columns represent what the true situation in the population is. And so if we start over here in the upper right, where based on our statistical test, we say that there's a difference, but in the population, there's actually no difference. And so we've made what we call a type 1 error, and we call the probability, or the probability of making this type 1 error is called alpha. So, and this is the p-value that you see in the literature when someone says that, p is less than 0.05 or 0.01 or whatever it might be. That's the probability of making a type 1 error. We're not so concerned with where there's no difference, and there's no difference in the population. But the other kind of error, serious error that we can make, is what's called a type 2 error, and the probability we assign to this type 2 error is called the beta error. And so this is a situation where, based on our statistical test, we conclude that there's no difference in the population, but in the true situation, there is a real difference. And so if we make this kind of conclusion, we've made what's called a type 2 error. And it turns out, as we'll see, that the type 1 error here is arbitrary. You can set it at whatever you want. Like I say, 0.05 is the most common one that you'll see, but you could set it at 0.06 or 0.1 or 0.03 or 0.001. The beta error, on the other hand, is also a function of what you set the type 1 error at, but the type 2 error, the beta probability, is also dependent on the sample size. And so we can decrease the probability of a beta error by increasing the sample size. And then this particular correct decision, where a difference exists based on our statistical test, and there is a true difference in the population, then we've made a correct decision, and that probability is 1 minus beta, and this is referred to as the power of our statistical test. And so the beta error here is really important in determining whether you've made a correct decision or not. However, the focus is on the type 1 error because you don't really want to make this kind of an error. This is, for the most part, considered the more serious error of making, where you say there's a difference, but in the population, there's no true difference. So in my example here of a treatment and control group, where the means are 81 and 86, and the standard deviations are 5 for the treatment group and 6 for the control group. And so we want to do calculate a t-statistic. We're going to do it just a t-test for means here. And so which t-distribution do we use? Well, it depends on the sample size, and our sample size is 5 for each group. So we have to calculate our degrees of freedom for our statistical test. And as I illustrated before, the concept of degrees of freedom is, what we mean by that is the number of components of a statistic that are free to vary. And so I've given the numerical example here from our data, where I have subtracted each value from the mean, in this case, the control group. You square each difference, and then we divide by, in this case, 5 minus 1 instead of by 5, or we divide by 4. So this is represented here by the first 4 values in our equation here can be free to vary, but once we know what those are, then the 5th one is not free to vary. So that's where we get our degrees of freedom as being, in this case, 5 minus 1, or 4. And so when we do our t-test, then what we're going to look at is our known variability, which is the difference in the two means, divided by our unknown variability, which is the standard error of the difference in two means. And so our degrees of freedom is going, our total degrees of freedom for our test here is going to be n minus 1 for each group. So in this case, we get, since there's 5 in each group, we would get 4 plus 4, or we'd have 8 degrees of freedom for our statistical test. And so here is just the computation, what the computation would look like, where we have our known variance here of 5 in the numerator. That's the difference in our means. And then the denominator is our standard error of the mean, or it's estimating our unknown variance. And so we're squaring the standard deviation, taking that times the degrees of freedom. That's divided by our total degrees of freedom, and then we multiply that by the reciprocals of the sum of the reciprocals of the number in each group, and so that gives us our standard error. And so if we divide our minus 5 here by this number here, we get a t-value of minus 1.4. And so if we look at our t-distribution that has degrees of freedom to 8, and the value of our t is minus 1.4, we find out that the probability associated with that, since it's negative, would be this part of the t-distribution curve over here, and it turns out that that's 0.0975, or we have a little less than 10% of the area under the curve, our t-distribution curve, and that gives us our probability, our p-value, of getting a difference this large just by chance. And so then we have a decision to make. Are we going to call this statistically significant or not? Well, again, I say it depends on which you're going to use as your cutoff for the alpha error. And so our calculation here is for what we call a one-sided test, 0.0975. If we do a two-sided test, then it's just 2 times that, and we get 0.1950. And so in this case, we would fail to reject the null hypothesis at the 0.05 level. And why would we do a two-sided test instead of a one-sided test? Well, because if we're doing research, then at least theoretically, we don't know which is better, the treatment or the control. It could be that the control is going to be better than the treatment group. So that's why we do a two-sided test. Basically because we don't know the direction of the difference between the two groups we're looking at. So what conclusions are we going to draw? Well, can we say that there's no difference between the treatment and control? The treatment does not lower heart rate? Well, actually, no, we can't say that. And the reason that we can't say that is because of the small sample size. And so what we can say is that in our research here, we found no evidence for a treatment effect. And so the conclusion that the difference could have occurred just by random sampling variability. And so because we have a small sample size, then we really don't have any basis for saying that there is a treatment effect, or even that there is no treatment effect. We just say that our results are inconclusive in this case. And so in this case, then we our conclusion would be that we have no difference between the two groups, and because we set our alpha level at 0.05, we would fail to reject our null hypothesis. Okay, so let me see, we're coming up on an hour here. So let me go over how we test for categorical outcomes and just do a simple two-category test here. Whether a test is positive or negative, whether, or it could be whether the test is positive or negative, whether we have disease or no disease, survival, dead or alive. And so what example here is, say, two treatments, say A and B, and treatment A had 84 out of 184 patients had a positive outcome, and in treatment B, we had 72 of 202 patients with a positive outcome. And so the research question we're asking is the proportion of positive outcomes different for A and B. So we do this in basically the same way that we did the t-test. So our proportion in A is 84 out of 184, or about 0.45. And our standard error, in this case, the standard error of a proportion is just the proportion times 1 minus the proportion divided by the total sample size. And so our standard error for population A is 0.037. We do the same thing for proportion, or for treatment B. The proportion there is 72 out of 202, or 0.35. We calculate that standard error, and then we subtract the proportion in A minus the proportion in B and divide by the standard error of the difference. And so it would, computational wise, it would look like this, where our standard error is the proportion times 1 minus the proportion times the reciprocals of the sum of the reciprocals of the sample size. And so our difference in proportions is 0.45 minus 0.35. We get 0.1001. The overall proportion is 156. That's 84 plus 72 divided by the total population, 386. So that's the proportion in positive in our entire sample. We take 1 minus that, we get basically 0.6. And then the sum of the reciprocals there is 0.01. So we calculate our normal distribution statistic of 0.1 divided by the standard error, and we come up with a value of 2.0. And so if we look at the normal distribution and the probabilities, or the areas under the normal curve associated with 2, we come up with a p-value of 0.045. And so in this case, if we had set our p-value at 0.05, then we could reject the null hypothesis that the difference in proportions is due to sampling variability, and conclude that treatment A resulted in a statistically significant greater proportion of positive outcomes than treatment B. In this case, 0.45 versus 0.35. So that's a test on how you would do a test that's for categories or for proportions. And so I think this will be the last one I'll go over before a break here. If we have a situation like we had there, where we had a 2x2 matrix of values, we can also compute a chi-square. And so to do this, it's the same kind of exercise in terms of what we're doing. It's just a little different for the chi-square calculation. So we have to calculate our expected values, which are row totals times column totals divided by the total sample size. And what we're going to do is subtract that from the observed frequency in each cell. And it turns out that this statistic that we get is distributed as a chi-square with degrees of freedom equal to the number of rows minus 1 times the number of columns minus 1. And so in my example here, I have the same numbers as I had before. And so my calculation for this chi-square statistic is going to first of all involve the expected. So for cell 1, the expected value is the row marginal times the column marginal, and then that's divided by the overall sample size. And so we do that for each cell, and then we subtract that expected from the observed, square that, and divide by the expected. And if we sum those up over the 4 cells, we get a chi-square here of 4.0. And you can see that we get virtually the same p-value that we did when we did it using the normal distribution. Okay, and just finish up here. If the study is prospective, then we can calculate what's called relative risk from the 2x2 table. And so that's basically looking at the risk factor and its probability of disease versus a risk factor being absent. And so those are the cell counts divided by the row marginals out here. And so in this case, we get a relative risk of 1.3. And so that means that if we have the risk factor present, we have that those that have a risk factor present are 1.3 times more likely to have the disease than not. And if we do a retrospective study, then we calculate an odds ratio. It's a slightly different calculation, and it gives a slightly different result. But we do this because in retrospective, we don't have a true estimate of the proportion diseased and the proportion not diseased in the population. And so I won't go through these in detail here, but you can follow the calculations. And so we get an odds ratio of 1.5, whereas our risk ratio is about 1.3. So it's fairly similar, but not quite the same. Okay, I think, let's see, wherever am I at here? And this is just another comments about the difference between odds ratios and relative risk ratios. Okay, let me stop there. I was going to keep going here, but it's taken just about an hour, over an hour. And so let's take a 10-minute break, and we'll start here talking about p-values, what they are not, and what they are. So I have a little after 5 after, so about a quarter after, 16 or 17 minutes after 12, we'll come back and pick up here.
Okay, yeah, so we'll see you all in 10 minutes. And for those who don't intend to, I mean, it's good to just check, but you don't intend to stretch, then make sure that you pull the file from GitHub. I'm going to put the GitHub link here, and then remember in the previous lecture, the professor showed you how to use, I think we used Git, I think, GIT software to clone the repo. Otherwise, just download the zip file and expand it and then have it. The files are also available on Code, but yeah, we'll take our 10-minute break. Come on, thanks.
How you doing, William?
Hello, Professor Musa. How's it going?
Good,
Nice
good.
seeing you. Yeah, I didn't see you because people don't
compute a test statistic and then get the corresponding p-value. Often, I think there's something of a misunderstanding of what the p-value means. And if you read a lot of literature, particularly medical research literature, it sounds like the p-value is the part of the study that determines whether you have, I guess, positive or negative findings. And that's interpreted, I think, or I guess I would say maybe it's a bit overinterpreted, because I think a lot of times the p-value is assumed to be the index of whether something is important or not. And that's not the case. So sometimes you'll see that the probability that people understand the p-value as the probability that the alternative hypothesis is true, or that the null hypothesis is false. Neither of those are the case. Neither of those are true. Or they look at it as an indication of importance or meaningfulness. And so oftentimes you'll hear the phrase statistical significance versus clinical significance. And so you can get something that is statistically significantly different, but from a clinical standpoint or from a useful use standpoint, it isn't meaningful at all. And another thing that you'll see in the literature quite often is when they get a really small p-value, though, call it highly significant. Well, that's kind of misleading too, because when you do hypothesis testing, it either is or it isn't. It's dependent on what you set as your alpha error level for your p-value. So if you get a really small p-value, what that means, the way that you can actually interpret that is that there's a very small chance that your results were due to random sampling variability or chance. But it's not zero, so. And then sometimes you'll see if you get like a p-value of 0.06 or something like that, they'll say there's a trend towards significant. Again, it's if you're the way that significance is meant to be used is as a decision to accept or to fail or to reject the null hypothesis, or to fail to reject the null hypothesis. And so if you set your p-value, your alpha L error level at say 6%, then 0.06 would be statistically significant. But if you set it at 0.05, then 0.06 is not significant. So as we talked about before, it's the probability, the p-value is the probability of obtaining a test statistic, whether that's a t, a chi-square, a normal distribution, z statistic, that you obtain a test statistic is large or even larger than that which is calculated, and assuming that the null hypothesis is true. And again, the idea here is related to the concept of repeated sampling. If you were able to sample over and over again an infinite number of times, this is what you would get. And it's also dependent on the sample size. And so we'll talk about that, probably next week. But primarily just remember that the p-value is arbitrary. And even though 0.05 is sort of the standard used in a lot of research areas, it can be set at something other than that. Maybe you want to set it at 0.01, but regardless, whatever it's set at, that's an arbitrary decision. Okay, so there was our break. I was pretty close to that. Okay, so I want to then take the last part of my time here talking about different statistical methods. And so we'll break these down into two different broad categories: parametric statistics and non-parametric statistics. And so parametric statistics assume that there's some theoretical distribution for the data or the test statistic, like it's normally distributed or chi-square distributed. Non-parametric, of course, that means that we're making no assumptions about the distribution. So I'll start out looking at correlation. And basically, when we talk about correlation, because this is really fundamental to all statistical tests, that at the simplest level, correlation is assessment of the linear rank ordering of two variables, how the values of one change in relationship to the other. And this is quantified by the correlation coefficient. So if you have a correlation coefficient of 0, that means there's no relationship between the two. If you have get a correlation coefficient of -1, that means you have a perfect inverse relationship. That is, as the values of one are increasing, the values of the other variable are decreasing. And if you have a value of +1, then you have a perfect positive relationship. That is, if the correlation is positive, that means the values of one variable are increasing, as are the values of the other variable. So in terms of looking at a correlation here from a numerical standpoint, I have data here of 25 patients, measurements of cholesterol, their weight in kilograms, and their age in years. And so if we want to, say, look at the correlation between cholesterol level and age, and we calculate that out, we would find it's 0.84, which is a pretty high correlation. So that means there's a pretty strong relationship between cholesterol level and age, and it's positive. So as a person increases in age, their cholesterol level is going up. So in this case, what we're going to do is we're going to look at one variable as having an effect on the other variable, or in other words, we're going to look at one variable as a function of the other. And so in this case, we're going to look at cholesterol as a function of age. And so I've plotted some points here for each each individual their age and their corresponding cholesterol level. So this is one. And so what we're going to do then is we want to, in addition to looking at the correlation, the relationship, we want to look at the linear relationship. So we want to find a straight line that fits the data, that best fits the data. And this is going to give us more information than just the correlation between the two. So this is fairly detailed here, but so that you I want you to basically understand what we're doing when we do regression, really regression of any kind. So Y here represents the mean cholesterol level. Okay, so that would be represented by this horizontal line here. And so the question that we're asking, does age add any information to whatever the cholesterol level might be over and above the mean level? And so there's different quantities that we can calculate here to give us that answer. And so we'll represent an individual point, their age and cholesterol level by Y sub I. So that's one up here is a particular patient. So their age about 60 and they have a fairly high cholesterol level in the 400s or better. And then our straight line here, which we call our regression line, will represent by Y prime. And so this is a theoretical line, you might say, or we'll call it a theoretical curve, even though it's a straight line. And so what we can do is we can find the distance between the individual value for age and cholesterol and look at that distance to the mean, okay, to the mean level, which is about 320. We can then look at the distance between the predicted value, the Y prime, and the mean. And then we can look at the difference between the observed value and the predicted value on the regression line. And so you can see that what we've basically done here is we've partitioned this distance into two separate distances here between Y and Y prime and the mean. Okay. And so we can then calculate what's called a sum of squares. And so the distance between the observed value and the mean value, this distance is equal to this distance plus this distance, except that we're going to square them. Otherwise, we'll come out with a value of 0. Okay, so that's why they're squared. But that's basically what this is. The distance between the observed value and the mean is partitioned into two different components. The difference between the observed and the regression, or the predicted and the mean. So we call this the total sum of squares. That's this part of the formula. This is called the sum of squares regression. In other words, the difference between the predicted value and the mean value. And then the difference between the observed value and the predicted value is error. In other words, based on our regression here, we predicted that this individual would have, at this particular age, would have a cholesterol level of about 380, but in fact, it's over 400. So this is actually what we call our error, or sometimes referred to as a residual, the difference between our observed and our predicted. And then, as you can see, then the total sum of squares is equal to the regression sum of squares plus the error sum of squares. If we divide the regression sum of squares by the sum of the regression plus the error sum of squares, we get a value called the R squared. And what is this? Well, this is actually the correlation between age and cholesterol squared. And so if we take the square root of r squared, we'll get the absolute value of r. And whether the correlation itself is actually positive or negative would be depending on which way the line slopes here. So here we have a positive slope as age is going up, so is cholesterol. If it was the other way around, cholesterol was going down and age was going up, then the correlation would be negative. So we don't really know the direction here from doing our regression analysis, but the square root of the r squared will give us the absolute value of the correlation. Okay, and so when we plot these, then we get a regression equation, and this line represents our fitted values and then our predicted values. And then basically you can see that some of the observed values are very close to the predicted value, but some are not quite so close. And so then we get an equation, a value of cholesterol in relationship to the age. And so it turns out that the regression equation is 102.6 plus 5.3 times age. Okay, well, what does that mean? Well, the first number here we call the constant or the intercept, and that's the value of, in this case, cholesterol when age is equal to 0. But of course, zero age is kind of a nonsense value here, so we usually do something else to make it more reasonable. But the 5.3 coefficient here that's multiplied by age, this is referred to as a regression coefficient, or in a simple linear analysis like this, that's the slope of the line. So what that means is that for every year increase in age, cholesterol goes up by 5.3 units, in this case, mg per 100 milliliters. So our regression equation gives us something, or gives us more information than just the correlation coefficient alone. It gives us this intercept point, and which in some cases might be important. In this case, it's not so important, but it gives us the slope. In other words, the change in your dependent variable, in this case, cholesterol, with every unit increase in age. So what that means is that you can multiply any age along here by 5.3 and you would get the predicted value that would fall along this line. Okay. And then, of course, we can compute a confidence interval for our regression line because there's variability there. And so this would be the 95% confidence interval of our regression line. And you can see that what happens here is that in regression, the confidence interval is not, or the upper and lower bounds are not straight lines across the entire range of age here. They're smallest at the mean age, which is around 40, but as you get near the extremes, the confidence interval becomes wider. So if you see a regression line in the literature that has straight lines here for the confidence, excuse me, the confidence interval, then they've not computed it correctly, because it should have this nonlinear look to it. Okay. So the relationship that we looked at here, the example that we looked at here, cholesterol and age, that's what is comes under the heading of what we call the general linear model, or GLM, that you probably have heard of. And so basically, this is our equation here where we have a dependent variable that's modeled as a function of some independent or variable or combination of variables. And so we represent this by y being our dependent variable here, and then the b's are regression coefficients. So the b sub 0 here, that's our constant. So in our previous example there, that was what, 102 or something like that. And then the regression coefficient for each covariate or independent variable that we have in our equation. But the point here is that the y is always a continuous outcome. And x's represent the covariates, and the b's or betas are the estimated regression coefficients. And so when you see an equation like this, where you have more than one independent variable, the interpretation is that the beta coefficient here represents the change in y for every unit increase in x. So when you have multiple independent variables, they're adjusted for all the other independent variables in the model. Okay. Now, in the general linear model here, the covariates or the independent variables can be a mix of continuous, ordinal, or even categorical variables. And so the statistical test that we would do in this case is we're going to test whether these regression coefficients are 0, or if they're different from 0. Because obviously, if these regression coefficients are 0, then whatever the quantity, it has no impact on y. So this would result in 0 wherever the regression coefficient is 0. And so the regression coefficient then can be positive or negative. And you can have, as I say, a mix of continuous, ordinal, or categorical variables. So in the general linear model, there's some special cases, one that we've already looked at. So if the x here is dichotomous, it's either, say, a treatment control. You have two groups, then this represents a t-test. Okay. And so if the independent variables, the x's here, are all categorical, then we have what's called analysis of variance. And the x's here can be either dichotomous or they can be categorical. It doesn't matter. If some of the x's are continuous, then we have what's known as analysis of covariance. So then, so what if we have an outcome that's not a continuous variable? And so if we have a dichotomous outcome, success, failure, dead, alive, positive or negative, then we will do what's called logistic regression for our analysis. And now what we're going to model is the probability of one of the dichotomies. So if you have, say, a treatment and control group, then maybe you're going to want to look at the treatment group as being coded 1 and the control group is being coded 0, so that we have a dichotomy there. And so the probability is, in this case, the exponentiated outcome y divided by 1 plus the exponentiated y, where y can be either a very simple or a more complex regression equation, just as we had in the linear case, where we have the same interpretation here. And so when we get this equation where y is a dichotomous outcome here, and we exponentiate the regression coefficients, then we get the odds ratio. So again, we can see that what sort of difference here is that we're predicting a probability, not a continuous outcome. We're predicting the probability of being in one category or the other. And so our statistical test here then is whether our regression coefficients are different from 1. Okay, because if the odds ratio is equal to 1, then that means that the odds of being in one group or the other, or having the outcome, are the same in both groups. And then when we compute a 95% confidence interval for odds ratios, if that interval includes 1, then we say that the odds of the event in either group are statistically the same. So that's slightly different from the general linear model, but when we do what's called the generalized linear model, we're looking at a different kind of outcome, an outcome that's measured in some other way other than continuous. And so just as we looked at before, we can have a special case of logistic regression where if the X is dichotomous, if the independent variable is dichotomous, then we just end up with a 2x2 contingency table that we looked at earlier. And then we can do logistic regression with more than just dichotomous outcomes. We can do what's called order logistic regression, where the outcome is ordinal in nature, multinomial logistic regression, where Y is nominal. They're in categories, they're not particularly ordered. You might assign them a number, but the ordering, or there's no order to the categories. And then we can do what's called Poisson regression, where the outcome is a count over some particular time period. And so, for example, we might look at ICU infections over a 3-month period, or some sort of outcome like that, where the outcome is just a count. And in this case, we get, for Poisson regression, we get regression coefficients similar to logistic regression. And if we exponentiate them, we get what's called an incident rate ratio instead of an odds ratio. In other words, a ratio of 2 rates. Okay, and then the time to event models, which are sometimes called survival models in manufacturing. I think they're called failure time models. But we have, in this case, an event, which is dichotomous. And then we have the time to the event. And so that implies that you have to have a point of origin and that the event has to occur at some point in time. And that the event, the terminal event, occurs after the start. In this case, we have some other issues, or another issue to think about, and that's what's referred to as censoring. Because if we are following, say, patients, cancer patients or heart disease patients over time, some patients might be lost to follow-up or drop out of the study. So the exact survival times are not known, but we can still use the time that the patients were being followed or were in the study to use in calculating our survival function. And so the survival function is a probability that a patient survives from the time of origin to some point beyond that particular time point. In time to event models or survival models, we also calculate what's called the hazard rate. And that's the probability that a patient dies at a time t that's conditional on having survived to time t. In other words, another way of saying that, it's the instantaneous death rate or failure rate for a patient that survived to a particular time. And the two, if you know one, you can calculate the other. and given the way in which they're related there, the hazard function and the survival function. And then we also talk about the median survival time, the time at which the survival rate is 50%. And so I want to use any small example here. So we're going to calculate what's called the Kaplan-Meier survival function. In other words, we're going to calculate the cumulative survival rate over our time period here. And so we start out at time 0 and we're going to 36 months. And we have these patients here that have, oh, this would be their age, yeah. So for our calculations here, that's not relevant. But so at time, oh, this is not their age, this is the number of patients. So we have 74 patients starting out in our study. And so at time 0, there are no deaths, nobody's dropped out. So the proportion surviving is 1, and the cumulative survival is 1 at time 0. Okay, at 7 months, we still have 74 patients, but we have 1 death. And so now the proportion surviving is 73 over 74, or is 0.9, almost 0.99. And then to calculate the cumulative survival, we just multiply the previous cumulative survival by the proportion surviving. So it's this 1 times 0.98. That's why we get the same value over here for the cumulative survival. Then at 11 months, now we don't remember, we only have 73 patients in our study. And now at 11 months, we have another death. So now our proportion surviving is 73 over 74. We get this. And then now our cumulative survival rate is 0.9865 times 0.9863, or we get 0.973. And so on down our survival times here at 12 months, 18 months, and so on. And you see at 28 months, we have 4 deaths. We also have 1 censored. Okay, so we, at month 28, we actually lose 5 points. So at month 36, we only have 56 patients left in our study that are have either died or have been lost to follow-up. So what we want to plot then is our survival, our cumulative survival proportions by our survival time. And so we get a graph that looks like this, and they have confidence intervals around it. And the horizontal or vertical dashes here represent patients that have either died or are censored. Okay, and so you can then at any particular time point read what the expected proportion surviving would be. And so you can see here that at 50% survival, everybody's actually surviving. So we don't really have a value where or a time when we reach the 50% level in this case. We can then also do survival where we have more than where we can have multiple covariates or multiple independent variables. And so in terms of the equation, it looks just like the regression equations that we had before, except now that we're going to take our baseline time 0 or a survival time and exponentiate the regression coefficient times times z, I'm sorry, whether it's 0 or not. And so again, what we're looking at is whether the regression coefficient here is 0 or is different from 0. And so if we have this kind of multivariables model of Cox proportional hazard, then we will get something that looks like this, where in this case, it's just different levels of the GSH. And so you can see that the higher the GSH level, the worse the survival rate. And so as you, and when you look at a survival function done in this way, you can see that these are all what we call parallel, and that's what the Cox model requires, is that you have proportional hazards, that the hazard rates are proportional regardless of or over time. Okay. So just a little bit about distribution free statistics or non-parametric statistics. So in this case, we make no assumption about the distribution of the outcome variable. And so you're probably familiar with, or you'll see if any statistics books on non-parametric statistics, different non-parametric statistics like the Mann-Whitney, the Wilcoxon matched pairs, Kruskal-Wallis, then for correlations, Spearman and Kendall correlations. And if you have correlated proportions, then McNeamer test. But the one thing about all of these tests is what they're actually testing are not the actual values of our outcome, but they're testing the ranks. And so all of these can be considered rank tests. And so they're non-parametric in the sense that, like for the Mann-Whitney here, if you do just a t-test between, for some outcome that say is continuous, but not normally distributed, or is really different from being normally distributed, then what's being compared, say in the two groups, are the ranks. So you rank all of the outcomes from high to low, and then get a rank score of those that fall in one group and those that fall in another group, and see where they fall, or see if there's a difference in the ranks. The thing is that these are somewhat limited, and so when sample sizes get to be around 30 or so or more, then everybody uses the normal distribution to calculate the p-values for these tests. So in that sense, they're maybe not truly distribution free if you have a fairly large number of subjects in your study. So what's truly non-parametric is when we do what's called the Bootstrap and the Jackknife. And so the Bootstrap is basically randomly selecting an observation from our sample data, and then we put that or a group back into the pool of data, and then we do again, we randomly select an observation and then put it back in the pool that can be selected. So you see that the Bootstrap may select the same patient any number of times, although it might be just a few times, but you have that possibility. But if you do the bootstrapping over a lot of times or many times, then you get an expected distribution of your outcome variable. The Jackknife is sort of the opposite of that. I'll have an illustration of that. Basically, what we do with that is we have our distribution of outcomes of data, and then we take one out and recalculate our statistics. And we put that one back in and take a different one out, and so on until we get through all of our subjects in our data, and then use a summary statistic of all those that we've calculated from leaving each one out. So this is the idea of Bootstrap. So you can see that we call sampling with replacement. So you have your sample over here, again, not your population, but your sample. And so you randomly sample that many times with replacement. And you sample, each sample is the same size as your original sample. So if this is, say, 100 patients in your sample, then each Bootstrap replicate has 100 patients in it, although some of them might be the same patient. And so in doing this, we can then calculate statistics, we can calculate confidence intervals, we can test hypotheses doing this. And so in this sense, it doesn't matter what the distribution of our sample is, of our outcome variable we're interested in here. We're just creating a distribution of that statistic. But this requires, depending on what you're doing, a fairly large number of replicates. So usually it's anywhere from 100 to 40,000 if you're doing hypothesis testing. But of course, on the computer, you can do that sort of thing fairly easily, and there's routines built into most software to do bootstrapping. I'm pretty sure there would be one in Python. So leave out one. This illustrates what we mean here. So if we have 10 observations, here's our statistic with all of them in there. Then we take out the first patient or the first subject here, and we recalculate our mean, and we take out the second, recalculate the mean, then take out the third, fourth, and so on. And so we have these 10 different estimates of our mean, and so that from the distribution of all these leave out one means we can get a 95% confidence interval, whether the distribution is symmetrical or not. And so that's leave out one, which again is fairly easy to program. Okay, then I want to finish up by talking about considerations for doing statistical analysis. So the first thing is what we call the effect size. In other words, if you're, say, testing a treatment and control group, what sort of difference is meaningful from a clinical or whatever the context of your research is? What's a meaningful difference, or what's a meaningful, odds ratio or a meaningful risk ratio? And then we need to know whether you have where we have paired or unpaired data, whether the data comes from clusters. I think I have an illustration of that. Then if we have non-randomized comparative effectiveness, that's where we actually want to compare, say, two treatments or two different groups on something, but it's non-randomized. Then we have the possibility of selection bias affecting our results, and how do we control for that? And then finally, one thing, I guess, in the end here, if you yourself are not a statistician, you may want to consult a statistician depending on the complexity of your study. So effect size is just, as I mentioned, it's the difference between, say, mean, survival rates, proportions, whatever. So the idea here is like when we're, if we're computing what sample size we need for a study, this is one piece of information that you need to know, is how big of a difference would be meaningful. And then what measure of variability do you have for this outcome? And so you can estimate effect size from pilot studies. You do a small study to get an idea of what differences there might be. You can get effect sizes from studies that are published that are doing similar things to what you want to do. Barring all that, we can do a best case, worst case scenario, given the type of data that you have. Then whether a data is paired or unpaired. Unpaired means that each data point comes from an independent entity. So like patients in treatment groups, you don't have the same patient in both the treatment and the control group. On the other hand, if we have paired data, then that means we have data from the same patient, or maybe it's matched pairs. So this is done in twin studies, obviously, where you have matched, even though they're different individuals, because they're twins, they're matched. If we do paired analyses, then usually that requires fewer patients, has more statistical power than independent groups tests or unpaired tests. But we also then have to deal with within patient variability. And then if we have both types of data, if we have both independent groups and we have paired data, like for example, if patients take some test over, say, a 3-month period, then we've got both independent groups and we have within patient variability that needs to be included in our analysis. So I have just an example here of a study we did some years ago where we looked at the effect of percutaneous coronary intervention on quality of life in patients with stable coronary disease. And so part of this was to look at these two instruments, the Seattle Angina Questionnaire and the RAND36, which are quality of life types of survey. And we wanted to look at the effect of whether or not they underwent PCI on their quality of life or their health status. And so this is in plotting the data over time. You can see that here's the two independent groups, but within each group we have patients measured, the same patient with measurements over time. So we have a different type of analysis that we would need to do here because it involves both independent groups and paired data, in the sense that patients are being followed over time. Then another consideration is whether we have what's called clustered or multi-level data. So what we mean by this is that we have, if we're doing, say we're doing a study, but what we're going to randomize is not individual patients, but we're going to randomize different health clinics or different hospitals. So in one hospital, all the patients are getting the same treatment. In another hospital, they're all controls or treatments or whatever. So the idea is that if some patients are coming from one particular hospital or one particular health institution, then their data may be correlated. And that's what we refer to as hierarchical or clustered data. And so in this type of analysis, we're going to consider two things, what we call fixed effects and random effects. Fixed effects are like our treatment control group. That's a finite set of levels that we want to look at. Random effects then would be, say, the levels of or the different clinical trial sites or different hospitals, maybe different geographic regions. And they would be considered random effects because they would be considered drawn from a potential or from a population of potential health institutions or hospitals that we could possibly draw from. So this, for the Curry's trial, this sort of illustrates the hierarchical nature of our data, where we have 3 different healthcare systems: the U.S. non-VA, Canadian healthcare systems, and then VA care systems in the US. And then within each healthcare system, we have different sites. Obviously more than 2 sites here for each one, but and then within each site, we have patients, individual patients that are randomized to either PCI or optimal medical therapy. And so these are all random effects, because there's obviously we're not getting all US hospitals or all Canadian hospitals. These sites are also a random effect, but the treatment group is a fixed effect, because that's what our interest is in, is comparing PCI versus OMT. And then we would have any number of patients at each site, which would also be, patients are always random effects. Okay, and so as I've already mentioned, the data from a given cluster might be correlated. In other words, we can't assume that they're independent, and this may affect our analysis then if we don't take it into account. And then I want to talk a little bit about non-randomized studies and looking at comparative effectiveness analyses. In other words, what we're comparing different, say, treatment groups. The pros of doing non-randomized studies that you actually get more data. The data probably already exists somewhere in a database or in EMRs. It's less expensive to do, and there's a claim that it's more realistic as far as clinical practice is concerned. The cons, of course, is that if you don't have randomization, then you have the potential for selection bias and confounding. So there's some ways that we can reduce selection bias. We can do case control matching, you can do covariate adjustment, we can stratify. And then a couple of things that we will go into next week, a propensity score analysis or inverse probability weighting, and then we can also do what's called instrumental variables. And so those are techniques or methods that are used in non-randomized studies to at least hopefully reduce selection bias. Okay, so with that, I think we're going to, we'll take another 10-minute break, and then William is going to get you going on doing Python coding for some of the data that we've looked at. So I will stop there, and if we don't finish going through all of the coding exercises, I believe then you can finish those up on your own, because I've taken up a little bit more time here than I had intended. Anyway, thank you for your time, and I'll turn it over to William at this point. And I guess I need to stop sharing my screen.
Yes, please. Paul, yes. Okay, so yeah, thanks a lot, Paul. And we'll take a 10-minute break, and then we'll come back and try and implement most of the theoretical aspect that Paul had graciously shared with us. So please take a 10-minute break, and then we'll be back. Okay, so we'll say welcome back. Hopefully, let me make sure my, I think everything is on. There we go. Okay, so I see everyone now. Okay, so welcome back, everyone. And we're going to go through some of the materials that Paul shared with us. So I hope everyone can see me and you can see my screen, right? Okay, I don't.
Yes.
I'll put it in the chat. Oh, good. Okay, thank you, Stacy. So the first thing we do, remember from Dr. Musa's class, Dr. Musa took us through the cloning the website, right? So the website that contains the materials, I posted it in the chat. So let me just repost it just in case. So make sure you have that. And for those who have Codio account, if you go to Codio, then you don't have to download anything. Just go to Codio and you would see something similar to what I see here. If you go to Codio, you will see a page for the so if you go to Codio, you're going to see something that looks like this. Yeah, and then basically you start the notebook on 3A. Okay, so once you hit that, it's going to load the notebook, and then you wait. So if you're using Codio, you don't have much of a struggle compared to if you have your own thing. Okay, so if you have your own file, then now if you're using Codio, just pull out the file that says student file, right? So there's going to be the student IPython notebook. If you pull it out, that would bring up something similar to this. And sorry for the date. Should have changed the date, but sorry for that. So, but the main thing you see is you see the student file. Now, if you are using your own environment, your own Anaconda environment, then you have to, basically what you have to do is go to the location on your computer, the file explorer, go into the location where you see mod 1, mod 2, you do a right mouse click. If you already have Git, which Dr. Musa took us through it, so we should have Git. If you do a right mouse click, if you're using Windows 10, then there's an extra layer. You have to click on new. I think you have to click on show more. They moved it into show more. And you see the Git bash here. Hit on Git bash here, it will give you something similar to this. For me, the fonts are small, so I opened one similar to that, okay? And what you want to do is git pull. I've done modification on my end, so if I try to do a git pull, it's going to give me an error. On your side, you're going to do a git pull. If you do a git pull, you're going to get a folder for mod 3, okay? And that will be the starting point, okay? So in mod 3, you then see the day 1 and day 2. And in day 1, you see this file, the IPython, both the student and the solution. For now, for your purposes, use the student file. Okay, this student file here. Now, the way to start your Python is through Anaconda, which Dr. Musa took us through. You start with the Windows, and then you type Anaconda, okay? And Anaconda Navigator will take you through it. I use the Conda prompt, and the reason for using the Conda prompt is that I'm then able to I'm able to change the different condas that I have and then select one that I want. Okay. In your case, you wouldn't have this problem. You see, in my case, I have different versions, different environments set up. So I'm able to pick one. And then once you do that, you do your Jupyter space notebook. Okay. If you hit, now the first thing you do actually, not Jupyter notebook, is you CD to the location where the file is. Otherwise, you're going to have a hard time finding it once you start Jupyter. Okay, so that's the reason I use this. So you do a CD to the location where the thing is, do a dir, make sure you can see the file, and then you do your Jupyter. Okay, so Jupyter space notebook. Okay, now once you fire Jupyter notebook, it's going to bring you to this page that looks like this. Okay, so you're then going to see the reason why you do a CD is in here is going to be very difficult to go back because the Jupyter notebook starts, the root is where you started, you call Jupyter notebook. Okay, so if your root is not nicely, if your reference point is far away from where your file is going to be a struggle. So I put my reference point close to where the file is and start my Jupyter notebook, so then I can see the files. Okay, and once you see the files, you click on the student file. Okay, once you click on the student file, it's going to open something that looks like this. Okay, and the way to tell it's a student file is there's going to be a lot of empty slots. Okay, there's going to be, and those empty slots are what you are going to try and fill out. Okay, so that's the difference between that. Now, so that you don't get too discouraged, because this is a learning process, what we've done is we provided a solution sheet. So the way the solution sheet is supposed to do is supposed to guide you. So as you try your hands on here, if you get an error, then you go to the solution sheet, and the solution sheet is nicely labeled. Okay, so if you go in here, it tells you that this is the slide 7 of what Paul took us through. So if you take what Paul took us through, which is the PowerPoint, and you go to slide 7, okay, so I'm going to fast, but stop me if you have to. You go to slide 7, you'll see the data there. Okay, so we made it so that you can combine the PowerPoint and the and some Googling of materials online and be able to go through. Okay, so this is slide 7. Okay, so we will start with making sure that everyone is on the same page. We've been able to clone the repo is the first thing. Okay, with a git pull, you clone it one time, and from that point on, with this from the beginning of that class, Dr. Musa took you through, you're going to just do git pull, git pull, git pull. That's all you do. Okay, so assuming the git pull went through, then, like I said, you're going to have something that looks like this with a day 3 added. You go to your day 3, and you should see that the file is there. If you're not able to do that, then just create a day 3 folder, go to the GitHub, download a zip file. Okay, so let me just do that. I know some students are going to. So you go down here, okay, you do a code, and you can download the zip file. Okay, download the zip file. All right, this is what we did. We just use a git pull, a git pull. With a git pull, you just copy this guy and put it in there. Okay, git pull, you just copy this, and you come down to your console, which will be this guy here. Okay, and so you do a git pull and you paste it like that, and to just pull it. Now, if I try to do it, my repo might be out of, I've made modification, so it's telling me I'm ahead of the head. So, but in your case, you're going to get something. Okay, so are we all set? So you can get a file here, you can download as a zip, and then double click or open it, and just copy and paste the file into the location. So I do this, and I go to mod 3, and I extract just mod 3, because you may have modified mod 1 and 2. So just mod 3, extract it to a location, okay, and extract it to a location that you can get back to. I put it on download, let's say here, and let's say I put it right here. I say, okay, I go to my download then, and I'll be able to then see the file there and take it and drop it where I want to drop it, okay? So that's how you do that. So are we all set as far as that goes? So here, and I go to mod 3, and that's the beauty of Git, that I can just come down here, just copy mod 3 and stick it where it belongs. Or I can just come day 1, copy the files, or even start Jupyter Notebook in here. Just that this is a download location and it's not your project location, but you can do that. You can start your Jupyter Notebook here, and when it's done, you move it to where you want it to be. So we are all set. We know how to clone. We know how to get the file, and we are ready to go now. So I'm going to use Codio, but interchangeably, I'm going to use Jupyter Notebook, just in case question comes up. Okay, so I'm going to use these interchangeably. It shouldn't complicate anything because Dr. Musa took us through. Okay. So now we have access to the student file, and the student file primarily, like I said, contains hyperlinks to the slides. Okay, so once you click on this, it takes you right in. Okay, and once you click on, if you get lost, just come to the objectives, you click and it takes you there. So if we recall from the material, just to re-emphasize what Professor Paul took us through, we have data that we want to create samples out of the data. Looking at this data, it looks just like an Excel file primarily, and we want to just pull samples out of it. The question is, how do we get this data into Python? Once you get the data into Python, these computations are just computations. This is the sum, and this is your numeric, the NumPy array, or this could be your data frame, and this is just a number. So this can easily be implemented in Python. So let's see how we go about doing that. Okay, so the way to do that is, since it's just a 1D array, 1D data, which is more like a vector, I'm going to use a lightweight data type, which is the array. So I'm going to put everything in an array, okay, and that's how you create it. Recall from Professor Musa's class, an array, the square bracket is what gives it away, a square bracket. And then this is a function call. So you take in, this could be redundant, but I like doing that. Okay, so primarily what you are doing here, let's say I open this, is you are saying A equal square bracket 1, 2, 3, something like that. But in my case, my numbers, I have more numbers, so I don't want it to go up the screen. And that is the reason why. Yeah, so if I do A, then I have that. Okay, and if you say the type of A, recall from Professor Musa's class, so this is a list, and that is why I turn the list into an array, okay, because I want to use some methods, okay, and now I have an array. Okay, so that's all I'm doing in here. So do baby steps, start with something small that you can easily comprehend, and then you grow it. Okay, so this, I started with this line, and then I started growing. Once I realized, okay, it worked. Alternatively, what you can do is, we have this data. We made, Professor Paul gave us a copy of this data, which is here. Okay, so we can use that as well. I don't want to download it, but the data, we have a copy of the data here, which is just a straight Excel. It's just a one column. Okay, one column with a variable name on top. Okay, and recall from Professor Paul's, someone said okay, so Nana, could you please help think Zane? So you can actually get that from, let me send you the, yeah, you can get it from the GitHub, or you can get it from the from Codio. If you don't have Jupyter Notebook set, then Codio will be the place to go, because the files are all there, and all you do, you click on it and you get it. Sure. Mine might take a long time to start, so I'm just going to, in the interest of time. Okay, so what we want to do is that we can either read the data, okay, or alternatively, so let's try this. Alternatively, what we can do is, instead of reading the data that we have, remember, you can always insert a cell and try things out yourself, okay? So we can do this, okay? Proceed and see that you can either load the data, okay, and display it, or you can load the data from the stored data set, okay, that Professor Paul gave us. And if you do that, you still get the data that looks like what we have. So So that's the second way of doing it. You've read the data, and that's a big wow. Once you get the data in Python, then the rest would be much easier. For now, don't worry about this reshape and sheet equal to 0, because the sheet equal to 0 means that if you have multiple sheets, I put it there so that in case you have multiple sheets, i.e. you have this sheet, you have this sheet, then you want to say, I want to put sheet 0. So the data we are using is from sheet 0 instead of sheet 1. Okay, so that's what this means. Okay, and then we reshape it so that it comes out in the form of a nice array here. Okay, so for the exercise, in the interest of time, we then want you to use Paul's slide to compute the mean, okay, compute the standard deviation by hand, use the notes given on Paul's slide 9, and the reason why we divide by n-1 is explained on Paul's slide. But we would like you to try this, and then we'll get back and then we'll go through it. Okay, there are two challenges. The challenge is that you, instead of just writing this as a sequential formula, we'd like you to do a function so that you can just call a function, just like we have np.mean, and then that we want you to also write a function that would hopefully do this for us. Okay, so we're going to take a quick, so your function is going to be like my mean, say. So instead of np mean from NumPy, it's going to be like your mean is going to be like a mean function like that, so that when it's called on the data, it gives us an output and the same, and then we want you to also plot. So we're going to take, hopefully we're going to give you about 5 minutes, try setting it up, try running it, and then we'll come back. Let's say at in 5 minutes time, just put 34. So about just before 1:40, let's come back. Okay. So if anyone has any problem, we can take you through this. We give ourselves 5 minutes, get to a starting point so that when you go home, you don't get stuck. There's also office hours you can utilize, but give ourselves 5 minutes. Let's give it a shot. Remember, there's the instructor file you can look at, but we would suggest, we recommend you try it on your own, and then use the instructor file. Okay, so remember the formula is the summation, and the sum is np sum. So you do np sum on this and divide by that this, and you should get that. Okay, and for the standard deviation, it's primarily np sum of a mean minus the individual squared divided by 144 minus 1, and then do np sqrt on that. If you're able to get a variance, that's fine. And don't worry about the function. The function will do ahead. So we take a quick 5 minutes and get back. Thank you. Okay, so Codio. If you're in Codio, all these have been installed, so don't worry about them. Okay, you just go down here, import your libraries, and then you can start. Okay, so like here, Control Enter or run, that loads the data, and then you can just start. Okay, so you can say something like mean, okay, equal, okay, and what is the mean? We're going to use NP for NumPy. We do the sum, we call from Dr. Musa, dbt, okay, and divide by the length. Okay, you can make it dynamic. LN of dbt. Okay, and then of course it's of no good if you cannot print it. And then there we go. So that should be how I will implement it. Okay. So use the NumPy for the sum, divide by the length, and that'll take it. And the standard deviation, you do the same thing, just take a look at the formula. Okay, so it's always look at the formula and write it out. So sigma is this NP sum. The mean you've already computed and subtract from each one of this and square. Okay, so you take the NP sum. So let's say my var or dbt okay, 40 var equal, okay, and then do NP sum of, and you take the individual, the mean, okay, so it's dbt mean, okay, minus the individual dbt, okay, and you basically up it up by 2, and if you want to be more specific, you group this guy, okay, and you divide by the length, like we did, len of dbt, okay, like that, and that, NP dot sum. It's a method. Okay, well, let's see why this is. I think I'm doing something a little tricky there. It's the individual. You see this type of error, and once you see it, just look at the solution that's been provided. Okay. I could have fixed it, but I want you to see that if you go on the literal side, you could get an error, and when you get an error and you are unable to decipher it, then just look at the solution. Okay, so just look at the solution, which would be the second one, to say instructor solution. Okay, so the solutions will be in here. Okay, there's a folder called solution. So if you click on that, the difference between the individual and the instructor is that the instructor one has everything in there. Okay. Okay, so we did a sum, we did the length, and we did a mean, and we got a mean. So here I took it in different steps. Then we got an output. Okay, so you run that, and it says you don't have that because we don't have the data. So you go up here and load your input. Okay, or use the run. The run is much faster. Okay, you do the run, and you then compute your mean here, and that will take you through that. And then the variance, this is what, okay, so it's saying here that instead of summing, we could then take this, which is another data, and then do the sum on the data, and then divide. So let's take that. So you take this guy, okay, Control C, go to the student, and instead of NP sum, you basically say the sum of this. Okay, so add it here. Okay, and take out the sum in front here. Okay, so this just taking you through the baby steps. Eventually, you will figure it out. Okay, so we have this all squared and then dot sum. Okay, so you go back and do that. This all squared. Okay, a square could be up or that dot sum and divide by the length, and that will get you that. Okay. There we go. I think I have more. What is this doing? Yeah. Sorry. This here, and this you're also going to encounter these types of things, but once it comes, just take it. Look at the solution. So let's try that. Say that there's an invalid. Okay, you go back here. And then, so if you're hopelessly stuck, then this is what you do. You just come down here and take this. Okay, I'm just taking you through. I could have fixed it, but I'm showing you how you can do that. Okay, so you bring it down there, run it, and then if it's all hopelessly stuck, there we go. Okay, so you're going to see these types of things. From the TA session, these are some of the experiences that students do have. So that's why I'm taking time to do that. Okay, so once you do that and it works, then that is a big plus that you've accomplished that. So now we've got, and then you take the square root of that. Okay, so in the interest of time, we're just going to go through quickly, and I'll show you how to utilize this. Are there any questions? Okay, so once you are able to compute the variance, then you take the square root of the variance. The square root comes from the NumPy. Okay, so from here, you just put NP square root of that, and that will result in that. Okay, and that takes you through the first part of the try it yourself. Are there any questions? I've provided references here in case you want to, in case the solution doesn't make a lot of sense. You can just open this, and this gives you exactly what we've done with example and a sample code. And this is how we learn from Python. Okay, so this in here they're creating a function, but you don't have to use that function. You can just go down, look at it, that they took the length, they took the sum divided by the length, and then they printed it out. Okay, and so that alternatively you can have you can import the statistic package, and then once you have the statistic package, you don't have to do any of those square root things. The p-variance would compute the variance for you as well. Okay, so we have these examples for you to use. Okay, let's go back on the if there are no questions, we go back to our solution, and I'll walk you through the statistics that Paul computed. So we went through here. We've been able to compute the variance and the standard deviation, and we are able to then print it out nicely, because there's one thing writing the code, and then there's a second thing actually displaying it. So I've given you ways in which you can display your output in a nice form using the print. Okay, so if I run this, it shows clearly, I'm telling you that the mean is that, the variance is that, and the standard deviation is that. Okay, the output makes things much clearer. The way you present the output makes things like. Okay, and then when you come to the challenge question is, how do you define a function that will do this? The function, as Paul said, you define the function name, and the argument it takes, and then what the function does, and return the output. Okay, so if I have this function defined, then I can run the data set on the function and get my result. That shouldn't stop you. Once you get your results, what you it doesn't make a lot of benefit. It doesn't give anyone a lot of benefit if you are not able to display the output in a nice form. So I have this, and I've created the results, and I'm going to just print out the results. Okay, so I'm here, and I run that, and then the results using a function. Okay, and then how do you plot? Paul took us through this. Dr. Musa took us through this. You have the data set, and you just call the plot function on the data set. The plot method comes from the PLT library. Okay, so from matplotlib .plot .pyplot, you import from matplotlib, you import pyplot as PLT. That's an alias to matplotlib.pyplot. So then you can call plt.plot on the object, and then plt.show will just show you the output. Okay, like that. Okay, now you can also use Seaborn. Okay, if you use Seaborn, it's the same thing. Seaborn on the object, and you get an output that looks like that. References are here for you to go through that. If you get down here, then you are through the challenge question. You've successfully gone through challenge questions. Okay, so now we go back to the student. So the next aspect is what the inference portion on slide 12 through 21. So basically, once you get here, the idea is that you then go back to the PowerPoint slide, go to slide 12. Okay, that's the inference portion, and with a video and everything. Once you go through, the question then becomes, how do you implement this? Okay, what I see here is I see data. So the question is, how do you get this data into Python, and then you'll be able to compute these modes? And so that's what we're going to do in here. Okay, so to do that, this is just a picture taken from Paul's note, but this shows you a step-by-step way in which you can capture data and you can sample from the data. Okay, so I'm using the seed so that it can be repeatable. If I don't use the seed, then my sample is going to change each time I run it. Let's see this. See, when I run it, I get 9-0. When I run, I get 5-4. But once I throw in a seed, then it will give me the same thing each time. Okay, 3-4, 3-4, 3-4, 3-4. Okay, so that allows me to repeat my experiment. This is saying from your population, I'm calling this the population is the data. Take two elements from this population. Take it at random. Okay, and so this time it took 3 and 4, and it took 3 and 4, and it took 3 and 4. So this is how you sample. Okay, now we talk about the seed. We're going down here, and then we're going to expand on that. So this was supposed to be your code. So when you go home, you're supposed to take a sample of length of size 12 from the BDP data set. Take 12 samples. Okay, so sample 1, sample 2, sample 3, sample 4, sample 5. Each time you get a sample of size n equal to 5. Okay, so we use a loop. Now let's see how that is implemented. So to implement that, what we do is we take, we are here. Okay, anytime I say take a sample of size n equal 5, see what will happen in here. This is saying, well, you know what? I'm going from 1 through the length of the data. I want to look at all the data. Each time I'm going to take the index. Okay, so let's print the index, what the index will give us out of here. Okay. Now, once I print the index, then I'm going to use the index to sample. Okay, so give me that. Okay, because I don't, okay, so that's what the index is doing, is return the index. So now I can now run the index on BDP and I'll get values. That's it. Okay, so these are the index and these are the, sorry, these are the index and these are the values. Okay, these are the index and these are the values. That says that when you look at the BDP data set, which is this big data, when you throw it in a vertical form, you take samples from each of the index provided, and then you put it in as an array or a list. Okay, and that is what this guy is doing. Okay, so each time I take a sample, I get a list. I take a sample, I get a list. Okay, and these lists, then I'm going to put them together in a nice form, and that is what Paul did. So here, I'm throwing a loop around it so that each time the list is generated, I print it out. Okay, and that gives you this nice output. Okay, which is similar to what Paul provided on slide 16. Okay, so now you've been able to get the data. Okay, so then we can easily compute the mean of each of these then, right? So we have a list and we should be able to compute the mean of each of the lists and stick it next to it. And to do that, this is how we do it. The print is a way to go. Okay, the print is a way to go. So let's run that. We have the sample that we've taken, okay, of size n equal to 5. We're looping through how many times, and each time we take the sample, we print it out, and also we compute the mean. Let me expand this a little bit so that we see. So we also compute the mean of the sample, and that's the only trick there is. And then I display my index, and then the list and the mean tagged onto it. Okay, and once I do that, I have something that looks like that. Okay, and this looks very similar to what Paul provided in here. You have a sample of size n equal to 5, and you display the sample and the mean. Okay, this comes to creating the Bootstrap sample. Okay, so that is the main thing. I think, like I said earlier, is getting the data into Python and knowing when to use a list, when to use an array, when to use a data frame, which was covered last week. Okay, this just re-emphasizing that it can be done. Okay, so now I have my data, I have my mean, I got my sample. So then I can compute the statistics on slide 19 that Paul talked about. Okay, and so all it is if I have a list, sample 1, I have another list, sample 2, I can compute the mean and put it sample 1, compute the mean, put it in sample 2, take the length, and then I can compute any statistic I want. Okay, so SEM by the formula given on slide 19, and then it's computed. Then the challenge we have to display. You display using the print. Okay, so if I run this, then I'm going to get a sample, the size, the mean, and then the SEM for each of the sample. If I can do it for this a small sample, then I can do it for the bigger sample. Okay, and I can even do more. I can tag on what the upper and the lower bounds are, and then I can now display it. Okay, so that takes us through the confidence interval for slide, I think, yeah, it was on slide 20. Okay, we're running slow on time here. So now I've computed all these statistics, okay, which then brings me very close to what Paul has in here, or Professor Paul has in here. I computed the mean, I computed the SEM, I computed the lower and the upper bound. I can display this one if I want, but I've gotten these statistics and basically constructed 95% confidence interval, okay, using Python. And those are the standard error of the mean. Okay, so I have that. Oh, sorry.
Yeah, William. I think yeah. So if you can maybe wrap it up in the next 30 seconds, so that we can. I mean, whilst I'm on it, so we have all of it. There's a database called All of It. So we have someone come to speak to us about it. So if you are on this and then you want to know about it, I think we are going to send the link in the chat area. Start at 2 p.m. I know it has been a long day, but if you are interested, you want to join, feel free to do so.
Okay, thank you, John. Yeah, so this actually is supposed to be something you do at home. So please go and complete the student file, okay? And as you get stuck, please take a look at the instructor file. And things are nicely labeled, so just go through it. We have office hours, so we'll be available to help you through this, and then we have office hours on Saturday. And so this primarily takes you through everything that Paul did today, including the Jackknife and all the other computations. Okay, thank you, John, and I'll pass you back to John.
All right, so let's all of us thank Paul and William for an excellent presentation on statistics and how to use Python to do some of these things. We have 3 more days to go, so I believe we are going to get more materials in the coming days. So again, thank you all for your participation, and then just make sure you sign in the attendance sheet if you need credit for it. Also, I think I saw Ibel. Is there going to be office hours TA session this afternoon?
Yes, they will. Yeah.
Okay, so there will be TA sessions. So again, check Slack for further information about it. Again, if you are not tired, and then I know some of you use Energizer batteries. If you want to join, feel free to do so at 2 p.m. Thank you all again for your participation and see you all tomorrow.
Thank you. Yeah.